Então, hoje vamos ver duas bibliotecas úteis para processar, agora de manhã, dados essencialmente numéricos, para se tiverem dados obtidos de aparelhos, medições e assim, que é esta biblioteca, o NumPy, que nos permite trabalhar com matrizes multidimensionais, vetores e facilmente fazer contas com esse tipo de estruturas. Vamos ver também o SciPy, que é uma biblioteca de computação científica, que tem também várias funções para fazer ajustes de modelos, para minimizar funções, enfim, e vamos ver alguns exemplos de como podemos usar estas bibliotecas para ajudar a processar os dados e a ajustar modelos teóricos aos dados experimentais. Esta biblioteca, o NumPy, tem módulos para criarmos vetores, matrizes e assim, funções para operar com essas estruturas de dados e também várias funcionalidades para fazermos operações algébricas básicas, tem geradores de números pseudo-aleatórios e vários elementos desses. Nós vamos ver alguns exemplos que podem ser úteis para processamento de dados numéricos. Um elemento base desta biblioteca, que basicamente o mais usado, são estes arrays, este tipo de objeto, o array do NumPy, que pode representar uma matriz de n dimensões. Pode ser uma só dimensão, um vetor, pode ser uma matriz bidimensional, etc. Nós podemos criar esse objeto a partir de uma lista ou de uma lista de listas, se tivermos uma matriz, usando esta função, array do NumPy. Portanto, importamos a biblioteca, normalmente dá-se esta alcunha NT para não ter que estar sempre a escrever NumPy, esta é standard, e depois usamos esta função, por exemplo, o array. Existem também funções zeros e ones, quem já usou MATLAB também está habituado a usar estas, para criar matrizes só com zeros, só com uns, matrizes n-dimensionais. E depois nós obtemos um objeto que gere estes dados, este objeto do tipo array, que nos permite fazer coisas como multiplicar todos os elementos por um certo valor. Por exemplo, se fizermos este vetor vezes 3, ele vai multiplicar cada elemento do vetor por 3 e devolver-nos um vetor com a mesma dimensão. Podemos fazer multiplicação entre vetores diferentes, desde que tenham o mesmo tamanho. Basicamente, a regra de multiplicação tem de permitir que o interpretador consiga descobrir qual é a correspondência entre os elementos. Portanto, se tivermos dois vetores do mesmo tamanho, isso é trivial, porque ele vai fazer a operação elemento a elemento entre os dois. Do you prefer English? Or?
Não.
Okay. E então temos este resultado em que vamos multiplicar este vetor, 1, 2, 3, 4, por este, 2, 3, 4, 5, e vamos obter em cada elemento o produto dos dois. Podemos também fazer este broadcasting, no fundo esta distribuição de outras operações, como por exemplo comparação. Se nós perguntarmos quais elementos do A são menores que 3, vamos obter um array também, um vetor, um objeto deste tipo. Neste caso não tem valores numéricos, tem valores booleanos, e vai-nos indicar quais é que são aqueles elementos que cumprem a condição. Portanto, nós podemos aplicar estas operações todas à matriz, ou ao vetor, ou n elementos, a matriz pode ser n-dimensional, e obtemos matrizes ou vetores, arrays da mesma dimensão, com os resultados das operações. Nós podemos também pedir o mesmo vetor, ou o vetor do mesmo tamanho, com os mesmos elementos, mas com outro tipo. Por exemplo, aqui nós criamos um vetor com valores inteiros. Se nós fizermos a divisão por 2 no Python 2 qualquer coisa, obtemos o resultado em inteiros também. Se nós quisermos, podemos pedir os mesmos valores, mas convertidos para valores fracionários, para estes floating points, float, e obtemos os mesmos valores nesta representação, já o resultado será diferente naquelas operações. Agora, quando nós queremos fazer este broadcasting, de distribuir as operações por arrays com tamanhos diferentes, temos de seguir estas regras. As dimensões são comparadas sempre da última para a primeira. E é possível fazer essa distribuição se um deles tiver de tamanho nessa dimensão, portanto aí é simplesmente repetido para todos os outros, ou então se o tamanho nessa dimensão for igual. Se quiserem mais detalhes do broadcasting está aqui, mas isto é a regra básica e eu vou ilustrar com alguns exemplos. Criamos aqui desta maneira uma matriz com 2 linhas e 4 colunas. Se tivermos já os valores e quisermos criar logo a matriz, podemos criar uma lista de listas em que cada lista destas dentro será uma das linhas e a lista destas listas todas será o conjunto de todas as linhas. Portanto, dá a matriz completa. E quando damos isto à função array do NumPy, vamos obter este objeto que nos representa a matriz e que podemos usar para fazer este tipo de operações. Notem que uma lista de listas não nos permite fazer este tipo de operações assim, porque é um objeto mais básico que nós já usámos, mas se nós, por exemplo, multiplicarmos uma lista por 3, ele simplesmente vai repetir o conteúdo da lista 3 vezes, dar-nos uma lista maior. Portanto, não tem o mesmo tipo de funcionalidade. Por isso, primeiro temos de criar aquele objeto array do NumPy para poder depois manipulá-lo. Depois temos isto, podemos criar aqui outro, por exemplo, neste caso temos uma matriz com 4 linhas e 2 colunas, a ideia é a mesma, temos 4 listas internas, cada uma especificando uma das linhas, e a lista dessas linhas vai dar as colunas. E quando usamos esta função array, obtemos a matriz. Uma funcionalidade que estes objetos têm é este campo T, é a transposta da matriz. Portanto, nós podemos facilmente obter a transposta, usar ali. So we can obtain the transpose of the matrix by using that uppercase T there. So if we do that with this matrix 2, which has 4 rows and 2 columns, we obtain this matrix with 2 rows and 4 columns. So it's simply the transpose. And we can broadcast these operations between the matrices. For example, matrix 1 multiplied by the transpose of matrix 2. Since they have the same dimension, this is the objects know how to apply the operation. And so we have, as a result, a matrix in which the values are the product of the corresponding values in the other two. We can also do broadcasting like this. For instance, if I divide matrix 1 by a vector with a length of 4, so this is a one-dimensional vector, the broadcasting rules will match this vector, which is only one dimension, with the last dimension of the matrix, which is the column. So it will apply this vector to each row and match the same column in both cases. So broadcasting is done from the last dimension backwards, and the match is either if the length is the same or if the length is 1 in one of the dimensions. So in this case, since in the last dimension they match, they have length 4, the objects know that they have to divide this one by this one, this 2 by this 2, and so forth. But then, since this is only 1 and we have several lines, this is repeated for all the lines. So we can divide each line of the matrix by a vector of the same number of columns and do it in one operation without having to do loops and so on. And this is much faster than if you actually do the loop and do this line by line, because this is implemented at a lower level and not at the level of Python, so this is much faster to do. We can also index these array objects. We can index them in the same way we index the list, but we can do it in several dimensions, for instance giving a splice or indicating the index in the row and the column. But we can also do this type of indexing. I create this array, I can use this range function to create an array from 0 to 9. We saw this range function when we did some loops, but you can use it to just create a list of numbers. And now I can create this array greater than 4, which is the result of comparing all these numbers to 4. So I have an array of booleans that will tell me true or false whether or not each of those values is greater than 4. I can do the same with lesser than 8, for example, and I have these arrays of true and false which tell me which values fulfill those conditions. And now I can use this array to index the elements I want. So these are indexes also of an element. 0 is the first one, 1 is the second, and so on. And I can use these Boolean values to indicate which values I want. So in this case, if I use greater than 4, this array here, to index my original array, I will not get these values. The false ones are ignored. I will only get the true, the ones corresponding to the true value. So I obtain this array here with only 5, 6, 7, 8, 9. I can do the same thing for lesser than 8. I can use these functions, for instance, logical AND, logical OR, which apply these operators to all the arrays. So if I use the logical AND with these two, greater than 4 and lesser than 8, then this AND will be applied element by element to all of these arrays. I will have an array which only has true in those elements that have true in both these arrays, and then I get only these parts, so the 5, 6, and 7. So we can index these arrays with with arrays of Boolean values, as long as they have the same length as the dimension we're using, and this makes it easier to select parts of some matrix or vector according to criteria that we establish. As long as we can write down the conditions, it's easy to extract those parts. So let's see an example of applying this. And the idea here will be to focus on mostly three things. First, repeating everything we saw last time, so all these basic elements of creating functions, loops, conditions, and so on, to help make this clearer, and this is something that takes some time to learn, so it's important to see many examples. Another point here is to show you with examples the application of these libraries. So in this case, I'm going to show some things we do with the NumPy library that makes it much easier to process this data. And then also another point here is that automating data processing also involves a lot of tricks to solve common problems, like getting something from the internet, or parsing files, or outputting some reports and things like that. So I try with these examples to cover some of those common problems, which even if you don't do anything related to the example itself, those elements are probably useful in different contexts. So to that purpose, I'm going to talk a bit about climate change, processing the temperature data. I have no experience with climate change, so probably I'm going to do some things wrong in the processing. Don't take this as a way to process climate data, but just as illustration for this functionality. This one?
Yeah. So when you have Mac 1 times Mac 2 with transpose Mac 2, we are not multiplying the matrix. We are multiplying
element by element. Yeah.
By element. So if we actually want to multiply the matrix.
You have functions for that, the dot product, the cross product, and so you can use those functions from NumPy. So by default, this is not in MATLAB. The default for matrices is the algebra rule. So you are multiplying. Usually, that ends up being a less common use of matrix multiplication than actually doing element by element, because we often use matrices not as algebra matrices, but just as a way to store data and to operate with the data. So in this case, this is a more common operation, so this is the default in NumPy. If you want to apply specific operations, for instance, the inner product of vectors, the cross product, and so on, you have functions for that. So this is, I'm going to use data for the World Bank. It has a series of links that you can use to get temperature data, average temperature data for different countries. this has a base URL, and then there is the country codes and that you can use. They are CSV files, and you can download for different countries. And the data that it has is the first column with the year, and the second column with the average temperature measured in that country. And we're going to I'm going to start by showing you how to obtain this data and then convert it into a useful matrix for us to operate with. So we're going to use this URL lib2 library, this module here that you already have installed if you installed Anaconda. And we're going to create a function to retrieve that data from the site based on the ISO code of the country. So these codes are the three-letter codes for each country. We can supply that code, and the function will get the data and return the matrix with that data. So this is a constant with the base URL. This is where we're going to get the data, the API from Climate Data API at World Bank, and then we have this long path, but this one is fixed. You can check the site and the documentation on this API. And we're going to obtain an object. This response object works like a file. The thing is that instead of reading from our local folder, for example, it's reading from somewhere on the internet. So we're going to use this library here, use the URL open function. This is similar to the open function that you use when reading the file, so it returns an object that works like that. Instead of giving the file name, we're going to give the URL for the resource that we want to read. So basically, this works the same as reading a local file, only you're using a different function to get data from the internet. And this you can use for this sort of pages. It's easy to use in any other context too. So we have the base URL, the country code, and then .csv, so that we obtain this final complete URL for the country that we want. And we obtain this object for reading the remote file. And now we could do it manually, read line by line, and then parse the file and so on. As we saw in previous examples, it would be the same thing. But we can also, since we're using NumPy, we can use this function, which is gen from text. It generates a matrix from a text file containing numerical data. So it's easy to read, as long as the file is in some tabular form, it's easy to read it all with just this function. So what this function needs is the object that gives access to the file, usually what we obtain with open, but we can also connect this to other different modules, such as this URL open. We have to specify the character used to delimit the columns. In this case, it's a comma, so the values are separated by commas. And we have this optional argument to skip some header lines. So sometimes, in this case, we have a header with year and data. We don't want that in our matrix. We only want the numbers. So we tell it to skip one line of header. Depending on the file, you may have to fine-tune these parameters. But basically, you have a function that easily reads a table of numbers into a NumPy array. And then we simply return this one. So basically, we have two lines of code to get data from the site into a NumPy matrix that we can then use, which is just getting the link to the object and then reading the data. One important thing, all of these functions, URL open, gen from text, and so on, these are functions that are already implemented. They are not basic elements of Python, and it's really not useful to try to memorize all of these things. Every time you want to use them, you just look up the documentation. How do I read the text file into a matrix or something like that? With Google, it's very simple. So as long as you understand the basics and you can look at an example like this and know how to use them, it's very easy to use all these resources. So don't worry about learning how to use each of these things individually. The idea is to be comfortable with the overall syntax of the language so that you can easily adapt the examples to your work and find from the documentation how to use them. Okay. So we may have a problem if we don't have internet connection. We may want to load our data from a local file. So we can do this. This is also to show the parallel between the two. In this case, we're going to use the open function to read a file that we assume is named with the ISO code of the country plus .csv that we have in our folder. And then we're going to use the same generate from text function here to read the file. So basically it's the same thing. Reading the file from a URL or reading the file from our folder is the same thing. The only difference is the function we're going to use and where the file is located. So in one case we have to give the complete URL to retrieve the file. In the other case we know the file name, and in this case we use the basic open function for accessing files. In this one we use the URL open function from URL list. Yes. Oh, sorry. This is if you need to break a line into two in Python, you can use the slash. This is not necessary if you have parentheses, because then the interpreter knows that everything belongs to the same line until the parentheses end. But if you don't have parentheses, you can say with a slash that you're continuing on the next line. So the reason I did this here is because if I put the URL in one line, I cannot show everything. So I split it into two strings, and I concatenate the two. So basically I'm having one string plus the other, which is the same as having the complete string. But I put this slash to tell the interpreter that this belongs to the same line. Okay? So if you have very long lines and for some reason you want to break them in some operator or something like that, then you can use the slash. If it's inside parentheses, you don't need to do that. So basically we have two functions that are very similar. One gets the file, the data from the site. The other gets the data from a local file. And now we can also write a function that gets the file from the site and saves it to a local file. This is not essential for this example in particular, but it may be useful if you are dealing with a large data set that is stored in some server and you don't want to be retrieving the data every time you run your program. So especially if you want to test things and so on, it's useful to have a local copy to work with it so that it takes less time to process, and then perhaps when you do the final run you retrieve everything again and run it again. So this is a sort of function that tends to be useful, getting things from the internet and saving them in your computer. This save from URL will need the ISO code of the country. It retrieves all the content from the site. So you see this URL open is that object that gives access to the file. I'm going to use this method from the object, which is similar to the read lines, but read simply reads all the bytes of the file. So I have a copy of the file in this array of bytes. And now I'm going to open a file for writing. I use this open function, the basic Python function. We already saw this when we wrote the report. I give it the file name, which is the ISO code and CSV, and tell the interpreter I'm opening this file for writing. So if the file does not exist, it's created. If it exists, then it's empty. All the contents are deleted. Then I write this array of bytes to the file and close it. So this way I created a copy of the file on the remote site by reading everything from the URL and saving it to a file. And now I can easily download everything. So I have this list of countries that I'm interested in, and I write a loop for each of these countries. So for C in country list means that C will take the value of each element of the list, so each of these strings. And then for each of these values, note the indentation here indicating that this command belongs inside the loop. So this is repeated for each value of C. I'm calling that function, reading the data from the site and saving it locally. So this way I retrieve all the data I want into my local folder.
If you wanted to keep it dynamic in the sense that you wanted to keep it updated, you would have to keep the connect to keep getting it from the internet, right? I mean,
Yes.
if we go this way, we cannot update it.
Yes,
Have
if
the-
you suppose that you have a script that generates some report or statistics or something like that. If your script starts this way, the first thing it will do will be retrieve everything and then process. The advantage is that you can separate this and make it optional. So sometimes you retrieve everything, sometimes you only process. Which, if you want to do something that keeps some report updated, you should always retrieve. But suppose you are developing that program, while you are debugging and testing things and so on, it may not be useful to keep retrieving everything each time you test. So in that case, you could retrieve once, test everything, and then plug in the part that does the retrieve. And I'm going to show that. Yeah, it will work for any web page where you can simply put in the URL and you have access. Some sites are more complex. For instance, if you want to do this with Facebook, it's a lot more complicated because Facebook gives you a series of JavaScript programs that then retrieve the data, and so there's a lot of more steps there. So for some cases, it may be very hard to do this. You may have to even interface with the browser and fool the site into thinking it's a person and not a machine or something like that. But in general, if you're accessing data that is meant to be easily accessed, then this should work because this is just each country is identified by this code on the site. It depends on how, because in this particular case, the site is structured with a fixed URL, and then you have the code for each country. So I'm using this code to identify the country because that's also what's in the site. And since I have this code, I also use the code for the file I have in my folder. Yes, I chose here. The way you build the URL will depend on the site that you're accessing and the rules for organizing the information. Okay? But the general idea could be the same. You have the URL, you read everything, and you save it to a file. And that should work for any static page like this. So now what we can do is to create another function. So this is just to illustrate one of those tricks. We want to make it easy for using our program, whether retrieving data from the internet or reading from a file. So we have this function, read temperature, that receives an ISO code and has this optional argument with the default value. This one tells the function whether or not to go search for the data online. Since we gave this argument the default value, note that we have the parameter here and we have equal to true. That means that by default, if we don't supply any argument there, any value there, it will assume this parameter to be true. So this is what happens if we call this function with only one argument. It will assume the online parameter to be true. If we give it a false here, then it will override the default and change the false. And what we do is, if this one is true, then we use the function that reads the country temperature from the website. It gives the ISO code to this function here, retrieves the data, and returns that as a metric. If online is not true, then we use the other one that reads from a file. So we have this wrapper function that easily decides whether to get things from the internet or locally. And now we can use this function to read the temperature of all the countries. So we have a list of all our countries. We also have this optional argument. So the idea is that if these functions are called without that online parameter, without specifying anything, they will get data from the site. If we don't want data from the site, we can put a false there, and data will be read locally from our folder. So I'm going to get the temperature of the table with the temperature from the first country here, and then I'm going to go from the second country to the end, read the temperature of that country, and then concatenate the original metric with each column with the second column of the matrix I'm reading. The idea here is that with the first country, I get a table with the years and the temperatures. Assuming that the years are the same in all countries, which should be the case in this site, then all I need for each additional country is to add a column with the temperatures of that country. And in the end, I have a matrix which has one column for the year and one column for each country with all the temperatures. And this is easy to do with NumPy this way. So I start by reading the temperatures of the first country so that I get all the years too. And then from the second country onwards, remember that index 1 is the second element of the list. So starting from the second element of the list of countries I want to retrieve, I read all the temperatures of that country into a temporary table. This temporary table has the years and the values for the temperatures. And then I extract only the values of the temperatures and I concatenate that with all the temperatures so far. So look at the syntax here. I want from this matrix, from this table, CSM, I want all the rows. So the first dimension I'm indexing has only these 2 points, so I have all the rows. And then I want the second column. And now here, the reason I'm putting this additional parenthesis here is that if you have a 2-dimensional matrix, the second column has only 1 dimension. So one column is a 1-dimensional vector. It's not a 2-dimensional matrix anymore. So by default, if you index one row or one column of a matrix, you get something that is only 1-dimensional. But what I want to concatenate is not a 1-dimensional column, but a 2-dimensional matrix that has only 1 column. This, for us, seems to be the same thing, because it only has 1 column all the same, but it's different for knowing how to match things together in 2 dimensions. Because a 1-dimensional vector is not horizontal or vertical, it's simply 1-dimensional. A 2-dimensional matrix with 1 column is 1 column vertical. Okay? So it keeps the 2 dimensions, it keeps the same orientation, and it has a vertical column. Anyway, this is not something to memorize, but something that you should keep in the background, because if you find you have problems matching vectors and matrices and so on, it may be because you're losing the dimensions somewhere in the end. Sometimes we want to do that. Sometimes we want to extract a column and have a 1-dimensional vector, but sometimes we want to extract a column and keep it a column. So keep it a 2-dimensional matrix with a vertical array of numbers. So this is the case here. We want to copy this column from our temporary temperature table and keep it a column, and then to concatenate that with our temperature matrix. And here we indicate the axis along which we're going to do the concatenation. Axis 0 would be the rows, which is the first dimension of our matrix. Axis 1 is in the direction of the column. So since we are adding the columns side by side, we're doing the concatenation with axis 1. By the way, when you're manipulating matrices, this axis argument appears quite often because you have to specify along which direction you want to do the operation. So remember that every time you want to do, for instance, averages or summing or concatenation or something like that, you should specify along which direction you want to do that on your map. So basically, this function will get all the data using the read temperature function, and then concatenate all the countries into a single table in which the first column is the year, and all the other columns are the temperature data for the country. Whether or not this function will get the data from the internet depends on this argument. If we don't say anything, if you only give the ISO code, or if we give the ISO code and true, it will get the data from the internet. If we don't want it, we can specifically say false in the second argument, and it will read from the file. So this is just an example of what happens when we do this sort of splicing. I have this matrix which has 2 columns and 4 rows, and if I ask for the second column, so I'm asking from this matrix all the rows and the second column, I get a one-dimensional array with the data on the second column. Note that this is not a matrix anymore. This is only the sequence of values in the second column. So it's one dimension. If I want to keep it in the same dimension as I had before, so I want to keep it as a column, I have to indicate a list of indices. So in this case it's only one index, but if I indicate the list of columns that I want, I will get the matrix. So in this case I indicate a list of columns with the single column that I want, and so I have this matrix here. Note that this is different from that one. This is a two-dimensional array with only one column, but it's still two dimensional. It has rows and columns, and this is a one-dimensional array. It only has one index to access. Okay, so now let's do a plot with the temperatures for our countries. We have this country list, which is the list of the ISO codes of the countries we're interested in, and now we get a table with all the temperatures for all the years by calling the country's temperature function with the country list. Since we don't add any additional argument, this function will assume that the second argument is true. It will assume that because we gave it a default argument. This is something you can do in general. You can add default values for your parameters in the function. The only condition that you have to meet is that once you have one parameter with a default value, all the parameters that follow must have default values too. The reason for that is that since we can give arguments into the parameters on the same ordering, so by position, the interpreter needs to know when you stop giving arguments which values, which parameters it will have with the default values. So after you have some parameters with default values, all the others that follow must have default values too, so you can just fill in the rest. Okay? So that is the only restriction. If you have more parameters here, all of them must have default values, or you need to change the order if you don't want default values on some of them. But once you do that, once you do something like this on the function, then you don't need to provide that argument, the value for that parameter as an argument. So in this case, we don't give anything extra. It will be assumed to be true, and the data will be retrieved from the internet. If we want to read from our local folder, we can just put there comma false, and then it will give false to the online argument, and everything will work okay too. So we're going to do a first plot with the temperatures for all countries. Since we have on the first column of our table the year, this will be the X value. So the X will be all the rows and the first column. And then all the series that we want will be all the rows and the second column until the end. Regardless of how many countries we have, this will work because the plot will create one series for each column. So now we have also a legend with the country list. The legend function in plot can take a list of strings that is as long as the number of series you have on the plot, and then it will assign those labels on the same order. There are also a lot of optional arguments that you can fill in. I'm just showing here a few examples where you want the legend to be. So in this case, in the upper left column, corner, how many columns in the legend you have, if it's only one, if it's split in 2, 3, and so on, the font size, whether or not to draw a rectangle around the legend, and so forth. So there are lots of things here that you have to look up the documentation, but this is just to let you know that you can customize the plots a lot. So you can just say legend country list, all the other arguments are optional, and then you'll get a default legend, or you can fine-tune it as much as you want. Then we have the same thing for the year, the X label, which is the year, the Y label is the temperature, and here in these labels you can use LaTeX syntax to indicate special characters or equations or things like that. So if you don't know LaTeX, this is not very useful, but if you know LaTeX, then you can easily put complex expressions in your labels this way. So in this case, I'm putting that circle for the centigrade, the degree symbol, and then a T. And then I save the chart, the graph into this file. So this is what we have for the years from 1900 to 2012, and we have the different countries represented here in different columns. So this is first part, getting the data and just plotting to see how it looks like. But if we want to examine the trend, we should put everything on the same scale, because these countries are at different latitudes, they have different average temperatures, but we can more or less see an increase here at the end, and if we want to make that clearer, we should rescale everything. Now, the things I'm going to do to rescale these, I have no claim to be dealing with this data correctly. So this is not about climate change or analyzing data. It's just to illustrate what you can do with NumPy, with this kind of data. So let's rescale everything to the temperature value of each country in 2012. So 2012 is the last data point that we have. We're going to put everything there, that is 1, let's say, and then we'll put everything relative to that value. To do that, we'll need to divide each column of our table, so each value on each column, by the value on the last row, which is the temperature for 2012. This is easy to do. We don't want to do that with the years stay the same, but we say that for all rows and for all columns starting on the second one, we don't want to divide by the year, we're going to divide the values there by the values on the last row and the second column onward. So see, the last row is -1, we are indexing from the end, and we have the second column onward. So this will be a matrix here which has all columns minus the first, we are ignoring the first one, and all the rows divided by the value at the end of each row. Remember the broadcasting rules that will align by the last dimension. So this is a one-dimensional array which has only the last row, and this will match the last dimension, the number of columns in this two-dimensional array. So this will be repeated for all the rows, this division. And then this matrix that is smaller than the original one because it's missing the first column will be copied into this part of the original matrix, which is also ignoring the first column. As long as the dimensions here are the same, NumPy can copy everything and place it there. It also follows the same broadcasting rule. So now, with one line, we rescaled everything to the value at 2012 for each country. And now we can plot again. And again, this is the same thing. I'm just changing the limits for the y-axis, but the rest of this is practically the same. And now we have everything grouped, everything scaled to 2012. Now, one problem with this is that since there is some variation in 2012, some of these plots seem to be a bit below what they should, the others above, because it's all dependent on the value of the last year. So if one country had a temperature a bit above average and another one below average, then the lines are not very well fit together. So we can do this a bit better. Let's try to fit all data from all the countries as close as possible to one of the countries just by doing a linear scaling. So we're going to scale the temperatures of all the countries to the first country. Of course, to do that, probably we should do it in Kelvin, not in centigrade or something like that, but we're not going to worry about that. It's just to illustrate what we're trying to do here. So basically, we want to minimize the difference between the temperatures of one country and some scale of the temperatures of each of the other countries. And we're going to compute these scaling factors for each country and then fit the lines together as much as possible. To do that, we're going to use this function, curveFit, which is a function that receives as the first argument some function that represents our model. So this is what we input the data into and get something out. And then we have the data, the x values and the y values, and then we have some additional parameters that the curveFit function will adjust in order to make the values coming from the model function as close as possible to the actual y values that we have on our data. So basically this is a function that tries to minimize the square error between the two by adjusting the parameters. These parameters, this is the result of asking for help on the curve fit function, but you can see more documentation there. But basically these parameters can be determined from by looking at the function we provide. This function should receive the x value first, and then a set of parameters, and return the y value. So this should be how our model function works. And the curve fit function will inspect the function we provide and determine how many parameters it has to fit. But in this case, it will only have to fit one parameter because we're going to fit the temperature of one country to the other by changing just the linear scale, and that is the parameter, the linear scale we're going to change on the table. So we need to write this function, the function that models what we're trying to fit. So this would be our function. It's simply, we obtain some temperature, we receive a vector with the temperature, we have this scaling parameter, and the output is just the vector of temperatures multiplied by the scale. So this is our simple model. We want to rescale each temperature to the temperature of some reference country. So this is basically the function we're going to use with curve fit. And now we have this function to rescale the temperature. We're going to receive a set of temperature values here, so the matrix with the temperature, and we're going to get the number of columns that we have on our matrix of temperatures. The first one should be the year, the second one is our reference country, and all the other ones are the ones we're going to feed. So we're going to create a series of scaling factors that will all start as 1. So this is just an excuse to use this function. This one function receives the dimensions of the matrix that you want and returns an array of that dimensions filled with 1. In this case, we want it to be only one dimension because it's just a scaling factor for each country, and we want it to have to be as long as the number of columns in our original table. So the first factor will be 1 because this corresponds to the column of the year, and we don't want to change the year. The second factor will also be 1 because it's the reference country, the first country you have on our table, so that one won't be rescaled. All the others we're going to compute using the curve fit function. So from the third one to the end, remember that index 2 is the third element here, we're going to call the curve fit function using this function here as the one that models our data, and as an input value, the x value will be, the x values will be the reference values will be the temperature of our reference country. This is the y values that must be output from our model, and the input values will be the values of the temperature for the country we are rescaling. So what we want to do is that once we give the temperature of the country we are rescaling to this model, and it outputs some temperatures after rescaling, it should be as close as possible to the reference country. So we are computing the scaling factor to put, say, the temperatures of Great Britain close to Portugal and so on. And then we're going to obtain the curve fit returns two values. One is the array with all the parameters that is optimized, and the other is the error in the end. We don't want the error, but we want the scaling factor. And since this is an array with only one element, anyway, we only want the first one, but this is always an array because this function can do this fit with multiple parameters. So we're going to put on the scaling factor for country IX the result we obtained from the curve fit. This means it's the best scaling factor for that country that brings the curve closer to the reference country, which is the first one on the table. So this sounds complicated, but the implementation is rather simple. We create an array of 1. For the year and the first country, we keep it at 1. From the second country onwards, we will fit it to the first country, compute the best scaling factor, and then keep the scaling factor there. In the end, we return the temperature, the matrix we obtain here, multiplied by the scaling factor. So the scaling factors are a series of values that has, it's a one-dimensional array which has many elements as the number of columns on the temperature. The first two are 1, so they don't change anything. The others are the rescaling factors for all the countries. When we multiply with the whole matrix of temperatures, we are rescaling all the countries that we need to change. So after we do this, we can test it. We're going to get the temperature. In this case, I've added this false parameter, so I'm no longer reading things from the internet. I'm reading things from the files in my folder. Then I rescale the temperatures. I give the table. It computes the rescaling, and then I store it in the table again. So this is the same variable because I don't care about the original. I just change all the values. And now it's the same thing, the same plot here, and we have this result after rescaling. So this one was everything rescaled to 2012. This one was everything fit together as possible, and we have them all fit to the temperature of Portugal, which was the first country on the list. So this is just to illustrate that something that, in general, you could probably assume that would be hard to implement, which is to find the best least mean squared fit for each country to the first one, and then rescale everything. You can actually do it in one function that only has one line for the model, and then calling the curve fit function with SciPy. So it's easy to do this kind of a stuff.
Do you always have to define the function when you create a scale model? For example, when you have a linear regression, you have any function that's already exposed as first fit?
Yeah. For linear regressions, you have them in SciPy already. I don't know for sure which function is, but you'll probably find. So this is a more generic thing to illustrate what you can do when you have any model. But you have specific function for the most common operators. But in general, yes, if you want to use a function that minimizes something or that adjusts something, you have to write that other function. But note that if your model is very simple, then it's really not a problem to have that function. This is just so that this is as flexible as possible, because you can adapt it to any kind of problem that you have. So now we have everything on the same scale. We can compute the average, for example, the average temperature after rescaling, and we are averaging over all the years after rescaling, and then again the same thing. This part is always similar, it's the plot. You can actually write a plotting function if you want, and you just send the date and write it all the same way. And this is something that simply receives the temperatures, changes the scale, creates a new temperature matrix which has the same number of rows as the original one, because we have the same number of years, but only has 2 columns. This is because the average yearly temperature over all the countries will only have one value for each year. So this average temperature table will only have 2 columns, the years and everything else. And now we copy all the years from the original table, which is all rows and the first column. We copy it into the first column of our new table. And the rest of it, so the second column of our new table, is simply the average of all the temperatures in the original table. So what we do is we ask for the average. This is a function in NumPy. We give this matrix, which is the original table, all the rows, and the second column onward. We don't want to average the years. We just want to average the temperature. And we say that we want to compute this average on the direction of the axis 1. So this is the second dimension of the matrix, which is along the column. So what we get here is a vector that has one element for each row, and in each of those elements, it's the average of that row measured along the column. Notice that this way we can do averages along the rows too, so have one vector that has the same number of columns, same number of elements as the columns, and averages over each of the columns. So we can do this in any direction that we want. In this case, we want to do it in the direction of the column, so we specify axis 1, and we get all the averages for all the rows in the matrix. Not the complete rows, because we are ignoring the first one, the first column, because that is the year. So basically this illustrates how we can select part of the matrix, then compute the averages and put everything on another part of another matrix. So now we have this matrix that has the average value over all the countries for each year after rescaling everything to the first country. And now we do the plot. This is the same thing, and this is what happens over the years on average over these countries after rescaling to Portugal. So we still have too much variance between years. We can do a moving average, slide a window of size n, and then average over n years in each place of the window. So the idea is that we have, suppose we have these values here, and we want to do a moving average with a window of 3. We would have for the first value the average of these 3 values, and then for the second value the average of these 3, and so forth. So this is the idea. We have on the total the number of moving average values we're going to have will be the length of the original vector minus the size of the window plus 1, because there is one, we have the window placed at the beginning and also at the end, so we have this number of elements in our moving average. That's the question. Okay. So this is how we can do it with a loop. We have the moving average vector is, we start with a vector of zeros that has this length. So the number of values that we receive, the length of the values, minus the size of the window plus 1. This is the number of values we're going to fill in. And then for each value in this range, starting from the window to the end, we're going to get this, compute the moving average at this position. So we start from the beginning, and then we sum this slice from the same index minus the window to the same index. So we're going to slice a part of the values with the size of the window. We add all the values there, and we divide by the size of the window. So this is the average on the place of the window, where the window is placed. This is where we place that value, and we loop through everything. This is there is an alternative way of doing this, which is much faster, which is using this cumulative sum function. So the cumulative sum will give us the sum of all elements up to each index. So in this case it's 1, in this case it's 3 because it's 2 plus 1, this is 6 because it's the sum of all those before, and so on. And when we want to do a moving average with the cumulative sum, we can simply use the difference between two values in the cumulative sum. This gives us the sum of all those intermediate values, and we can divide that by the size of the window. So, for example, in this case, we could do 10 minus 1 divided by 3, and this would be the 9. That would be the sum of the values there divided by 3, and so on. So we can do this without the loop. We can create a vector with a cumulative sum, and then from the index corresponding to the size of the window onwards, we just use the value of the cumulative sum there, and we subtract the value of the shifted by that length of the window. So we are subtracting from these values that are shifted a bit before. And since this is broadcast over all the array, we have all these subtractions done in one instruction. And then we just divide everything by the size of the window and return the values that we want. So basically, this is just to give you an idea that quite often things that you are doing with loops can be done also by using this broadcasting and vectorizing the operations using those broadcasting properties of the NumPy array. The difference is that usually it's easier to understand what you're doing in a loop, but then if you try to make it much more efficient, it can get a bit confusing. So start by doing things piece by piece, and if you have something that is too slow and slowing down your processing, then maybe you can rethink how to implement that and take advantage of this vector operation. Okay, so now we use a window of 10 years, we rescale the temperatures, compute the average, and then compute the moving average for that window, and plot the moving average over the year. So basically, we have this, we copy the average temperature here, and we compute the moving average for that average temperature using a window of 10. And now we're going to use the year and the moving average temperature there to do the plot. So the plot is the same thing again, and now we have a smoother plot. How smooth this one is depends on the size of the window, which we can vary. So if we use a larger window, we have it's more smoothed out. If we use a smaller window, it has more peaks. Another thing we can do is to try to fit a polynomial curve. This is also a common model for, in many cases, we can try to fit a polynomial curve to the data. So we get read all the temperature data into a table. We rescale everything to Portugal and compute the average. So now we have the average for all countries over the year. And now we're going to fit a polynomial curve to our data. So we can do this easily with the polyfit function. The polyfit function receives the x values, the y values, and the degree of the polynomial we want to fit, and then it returns the coefficients of the polynomial. So this is 0 is the coefficient for the highest degree of x, then the second coefficient is the one for one lower degree for x, and so on. So in this case, since this is a quadratic curve, this one is multiplied by x squared, this one is multiplied by x, and the third one is just a constant. The trick here is that if you're trying to do a polynomial fit with the years as the x value, you start with 1900, you go up to 2012, and this gives very large values of x, so the polynomial fit function may not work very well, because now you're using very large numbers. So what I did here was simply to count 1900 as the year 0 and put everything into more manageable numbers, or you can even rescale everything to 0 and 1. In this case it doesn't make much difference, but in general, if you're using numerical methods to adjust models, it's good to have your values around 0 and 1 and in similar scales, because if you have, say, the x values ranging from 10,000 to a million, and then you are adjusting things that only change in very small numbers, something like that, then maybe the numerical methods will become unstable. So this is what I do here. The vector of the relative years relative to the first one are just the years I have, the first column, minus the first year, the value of the first year. So I put everything counting from 1900 as if it was 0. Then I compute the polynomial fit. I compute the temperatures from the polynomial curve, and then I plot everything on the original year as the x-axis. So I'm going to plot the original temperatures as, so the rescaled temperatures as dots, and then a line with the polynomial curve for the same year. So this is the result here. We have, this is the temperature for, on average, for all the countries after rescaling to Portugal, and this green line here is the result of the polynomial fit, trying to minimize the error to all these countries. So this, I'm not claiming that the polynomial fit is a good one in this case, but this was just to illustrate different kinds of processing you can do with this data. So we rescaled all the metrics to the values of the last year. We did a fit for all the different temperatures using that curve fit function. We computed a polynomial and the moving average and so on. And this does not take much code. So each of these things, for example, the polynomial fit is actually 2 or 3 lines of code, just because we have to change the relative years so that we don't get numerical problems with the fit. But all of these things are easy to do if you use these tools and you know how to use these functions. Knowing how to use these functions is just looking up the documentation. So that part is easy. After you know the basics, just Google how to do these things, and you have lots of examples. So now I'm going to talk about something I know a bit more than climate change, so this one is easier. This is an example of a kinetic, Michaelis Menten kinetic model, which is for enzyme kinetics. So the velocity of a reaction catalyzed by an enzyme will depend on the concentration of the substrate, which is that molecule or that compound that the enzyme is reacting with, and then has those two parameters. Vmax is the maximum velocity of catalysis that the enzyme can do, and that Km is the concentration of the substrate corresponding to half the maximum velocity. And this basically defines a sigmoidal curve like this. So you have this, the position of the curve and the height of the curve is defined by those parameters. And here we have some data that we obtained by measuring the velocity of the reaction with different concentrations of the substrate. So we have this file. The first row is the concentration of the substrate. This is in some arbitrary unit. And the second row is the velocity of the reaction at that concentration of the substrate. So we need to fit this curve here, finding those parameters, Vmax and Km, in order to fit our data as best as we can. Now, one way of doing this, so before using computers, was to take the logarithm of that. This linearizes the equation, and we do a linear regression. Of course, then, when we do the linear regression, we are computing the quadratic error on the logarithms and not on the data itself, so there are some differences there, but this is one standard way of solving these problems. With computers, we can put the computer trying different values until it finds the best fit. So this is a more general approach that I'm going to talk about that does not depend on having a simple model that you can solve analytically in some way. So if you have a more complex model, then probably the only way we know how to solve it is numerically. So that will be the example here. What we're going to do is to define a cost function that measures the error between the model and the data, and then minimize that error adjusting the parameters. The minimization, we're going to use a function that we already have in the SciPy library, but we're going to first define the error function. So this is the cost function that we want to put as close to zero as possible. And we can do that by measuring the quadratic error on the velocity. So the assumption here is that basically the concentration of the substrate we can determine with great precision since we are preparing the solution. But the velocity, there may be some errors in measurement or in some effects that are occurring in the reaction itself. So we're going to use that, to assume that the error comes from the difference in velocity between what we would expect and what we observe. So if we receive the parameters here, so the parameters will be the two values that we want to change, Vmax and Km, and we have the substrate concentration and the velocity. We can compute the predicted values for the velocities using that equation there. So we have the first parameter, which is the maximum velocity, Vmax, times the substrate concentration, divided by the second parameter, which is this Km here, and added to the substrate concentration. The substrate concentration is a vector, it's not just one value. However, since we are using these NumPy vectors, we can do this multiplication over all the elements in one go. So we can easily write the formula this way, and since this is a vector and this is a scalar value, it's one value, it will get the vector with all the multiplications, and then the same thing for the division with a vector of the same size. So as long as we have the same number of elements on S and V, we can do this comparison. So now the cost, or the error here, will be the squared difference between the predicted and the observed values, and this sums over all the points. So this is the total quadratic error that we are outputting from this function. And this is the cost that we want to minimize. And we will minimize it using the minimize function from SciPy. So we import this from the optimized module in SciPy. And what we need to do for the minimize function We tell it which function it has to minimize. We give it an initial guess for the parameters, for the values it needs to change. So this vector, the size of this vector will determine the size of the vector the minimize function will give our cost function. In this case, we are trying to fine-tune two values. We start with a vector of size 2, and we are putting in an initial guess of 1 for each of the values. We also can give the minimize function additional arguments that we want to be sent to our cost function. So in this case, we have the substrate concentration vector and the measured velocities vector, and we want this to be just supplied to our cost function. So the minimize function will not look at those values, but since the cost function needs those values, it will give it to the other function. And now we can also specify bounds on the values of the parameters that we accept. So in this case, the Vmax and Km cannot be negative values. That would not make sense physically. So we say that for each of these parameters, we have two of them, we indicate a tuple with the minimum and the maximum allowed value. The minimum is 0, because we don't want it to fall below 0. The maximum is none, which means that we don't want to constrain how high it can go. But you can adapt this depending on the requirements of your model. Again, these details, there are also other options that you can use in minimize function. It has lots of possible arguments, but these details are something that when you need to use, you check the documentation and see how you need to fill it in. The important thing to retain here is for you to understand how easy it is to use these tools to adjust, to fit a model to your data, for example. So basically here what we need is this small function just to compute the error, which is basically writing down our model and computing the quadratic error, and then we need to set up the data and call our function. So if the data is a matrix with two rows, the first row the substrate concentration and the second row the measured velocity, we put this into two vectors, and then we call the minimize function. And now this minimize function will return an object which has a general report on how the function went. What was the final error, the number of iterations, the parameters it found, and so on. The parameters are these x fields, and it has a size of 2 because that's what we specified. We wanted to adjust two parameters. And so we copy this into a variable called Vmax and another one called Km, and we return those two. So now we have the result, what we wanted, the Vmax and the Km, that minimizes the quadratic error between the model and the data that we have. This is just to do the plot. So we create, this is a different example for plotting. We have, in this case, with the countries, we have lots of years. So if we plot the polynomial curve over these years, we get a smooth curve, since we have lots of years here. In this case, we only have a few data points. So if we plot the curve over only these points, we get something that has jagged lines, because we are just joining different points with straight lines. So one trick to improve this is to create the x value with more points than the data points that we have. So instead of just using those points, when I want to draw the curve, I put in more points so that the curve becomes smoother. So I use this function linspace, which gives me a set of evenly distributed points over a range, and I range them from 0 to the maximum substrate concentration I have in my data, multiplied by 1.1, so that the curve goes a bit beyond the end of the data. It does not end exactly on the last point. And I add for 200 points in that range. So now my x value for drawing my x-axis for drawing the curve has 200 points, and the curve becomes smoother. Then I want to plot this, so I receive the Km and the Vmax, and I plot the epsilon value corresponding to these x values. This is simply applying the equation here. So I have Vmax multiplied by each x value divided by Km added to each x value. And this gives me the epsilon values for the curve. And now I plot everything. I plot the curve, with a red line and a width of 2, and then I plot the data with blue axis, blue cross. These strings for formatting, if you use MATLAB, you're probably used to them. If you don't, then this is something that you can look up on the documentation, but it makes it easy to specify colors and the symbols used and so on. And also I can control the size of the marker, the width of the line, and so on and so forth. So this is what I get here. This is the curve. The curve was plotted over 200 points, so that's why it looks smoother. If I only plotted it over these points, it would be a set of jagged straight lines. Then I have the data points there, and this is basically what I use to calling all these functions that I wrote. I load the data, I obtain the parameters by adjusting the model, and then I plot everything and save it to a file. And these are the values that I obtain. So I have in these variables, I have the values that I wanted for my model. So this is an example that you can apply in general when you have some data and you want to adjust the model. You just need to define the error of the model with respect to the data, and then use the minimize function to find the best parameter. Now, another thing that it's harder to do without programming is to get an estimate of the error for this parameter. So I have a value, the best value for the parameters, but what does this mean? What is the range of possible values that I could obtain here? What is the error for my parameters? And we can do this easily numerically by bootstrapping. Bootstrapping is a general technique to obtain to make it create synthetical replicas of your data that have the same distribution as your data. So basically, if I could repeat the experiment 500 times, I would have different data points for each experiment, because the error will be those error factors will add up to different things, and I would have a range of data points, and I could compute the curve for each of them and have an idea of the error in my estimate given the kind of experiment I'm doing. But doing the same experiment 500 times is not very risky. So with bootstrapping, what you do is you use the data that you have and you resample from that data with repetition. So you have some repeated values, but others don't appear, and you create replicas of your data as if you were repeating the experiment. And they should be distributed in the same way because you're sampling from the actual data that you have. So the probability distribution of those replicas should be the same as the universe of possible experiments you could do. So this is easy to do with a bit of programming. In this particular case, we don't want to do bootstrapping, standard bootstrapping, because although we can assume that the errors of the velocity are random, the values for the substrate concentration, we choose them in purpose so that we can get a good representation of the curve where it curves more and so on. So it would not make sense to sample randomly from this data set, because then we would have points on the wrong place and we would not have a good curve. But we have a variant of bootstrapping which is called residual bootstrapping. So this is what we're going to sample. When we compute the best curve, each of our data points has some error. It's either above or below the curve. So these are called the residuals. And we can assume that these errors are random. So this point is here, but it could be there or somewhere else if the error had been different. So what we're going to do, bootstrapping is on these residuals. We're going to take all these residuals into a vector. We have a pool of residuals. And now we're going to generate new data, always in the same substrate concentration, but each data point will be affected by a random residual that we're going to choose from our pool of residuals. So this way, we are imitating what would be a series of experiments where the errors would be approximately distributed in the same way as this particular experiment. So what we're going to do is we create new replicas of the data by picking random residual values for each point relative to the best curve. And now for each of these replicas we can compute a new curve, because the points are at different positions, the curve will be slightly different. And if we do this a few hundred times, we can have an idea of the range of values or the distribution of values for each of the parameters that we have. So this is what we're going to do with residual bootstrapping. We create this function that receives the parameters of the origin of the best curve we found from our data, the data itself, and the number of replicas we want to create by bootstrapping. Now we're going to compute the predicted values, so this curve is the predicted velocity value, from the parameters we get here and from the original data. So this is the basic curve, the best model that we have. And we're going to compute the residuals. The residuals are the difference between the actual measured velocities and the predicted velocities from the model. So we have all these residuals, these values here, for all the points. And this is the pool of values we're going to draw randomly from to generate the new replica. So now, for each replica, we're going to ask this this library of NumPy, which generates pseudo-random numbers. We're going to ask for numbers between 0 and the shape of this matrix. So shape 1 is the number of columns on the matrix. So basically, this is the number of data points that we have. And we're going to ask for a vector with that number of points. So this, if we have 10 data points, these are values at random between 0 and 9, and we ask for 10 of them. They may be repeated, but it's not a problem because this is sampling with representation. So we have these random indexes. And now, to create one replica, we simply add to the predicted values the residuals obtained at those indexes. So we are using this random set of numbers as indexes to pick random residuals and add to the values. So this creates a replica by drawing from that pool of residuals and changing and adding to the predicted value. And now we're going to do the same thing we did before. We use the minimize function to get the best parameters for this synthetic data set now, and we add the parameters, we append the parameters to our list of parameters. So now we get 500 sets of pairs of Vmax and Km, each one obtained by a residual bootstrapping replica of our original data. And now we can compute the mean of all these parameters and the standard deviation of these parameters too. So we have an idea of where they are on average and how spread out they are. And this spreading depends on how large the residuals are, which in turn depends on how scattered our data is relative to the curve. So if we have very good data close to the curve, there will be a much smaller spread in these values. And this is a representation of all those curves. So the blue one is the best curve we fit to the original data. So this is our best estimate for our parameters. But the others give us an idea of how spread out the curves can be if we assume that we have those random errors on the residuals and we generate those 500 values. And we can also do a histogram for the parameters over these 500 replicas. So we have these, most of the time this is Vmax and Km, most of the time they are here close to the mean, the average, but we see that they also spread out quite a bit. So we can get from here like a 90% confidence interval or something like that to have an idea of how our parameters are spread out. This is not easy to do on a spreadsheet because we would have to do a huge spreadsheet to do all these replicas, but it's quite easy to do with a bit of programming. You just need to do a loop and repeat, and this n can easily be 1,000, 10,000, whatever you want. You just wait for a bit and get the result. So to sum up, this is the three main ideas here was to do a bit of revision of functions, loops, conditions, and so on. By this time, you should be a bit more familiar with that, at least to be able to look at an example and understand it easily by looking at the code. We also saw specifically NumPy and SciPy, so basically the most important libraries for working with numerical data. This is something that probably all of you will have to do, even if you're dealing with categorical data or other kinds of tables. Eventually you'll have to compute statistics and present some models and graphs and something like that. So you'll generally have to use matrices, vectors, and it's useful to know a bit about these tricks that can simplify the code a lot. And then we also saw a few other tricks like creating functions with optional values or default values for the arguments, so that you can easily use the function without having to give all the arguments there, retrieving data from the internet, saving it locally, and so forth. So these are the kinds of more general tricks that usually you have to keep learning from examples and from looking things up on the internet, but if you know the basics, it's easy to understand these examples. So you have on chapters 4 and 12 of the book, you have the more details on the NumPy array, and you can also look at the documentation and examples online. So this is usually better even than the book, because you have lots of tutorials, you have examples, you have code. So after you go over this first barrier of looking at code and it seems like it's a strange language, after you start getting used to it, then it's easy to learn these things from all the examples.